Now let's move on to the application of optimization to revenue, cost, and profits, which are key theme of business. Okay. In this section, I will be focusing on maximizing revenues. So revenue is expressed as price by quantity, right? Revenue is your total income from sales, and the price is a unitary price, and here the quantity is how much you successfully sold. So unit price by quantity, that's your total income. And here we need to input the inverse demand function for price, which means price is expressed as a function of quantity. Why is that? Because quantity is what you can control as a firm, right? You can easily change your production plan to produce more or less, rather than persuade consumers to accept a higher price or not. So it is habitual in this class and in your future in econ and business classes that we consider quantity to be the choice variable. So here, I'll just put this as an underlined red remark here to remind you. And here we are to maximize revenue. So we are actually doing exactly the same thing as we did previously, as we are optimizing functions. The only difference is here, previously we were talking about a general function, and here the function is specified as a revenue function. So we're going to follow the first three steps, which is to solve the first order condition. Okay, so now what we are doing is we take the first derivative total revenue with respect to Q. And we set the first order condition equal to 0, and we solve for the root of this first order condition. So the first steps are actually solution of first order condition. And then we need to check the second order conditions to make sure you are actually solving for a maximizing problem, not a minimizing problem. So here is the example. P equals to 80 minus 2Q. And here we are to find the quantity that maximizes the revenue. So I'm going to switch to my document camera to demonstrate the solution. So first, you need to figure out the total revenue function, which is P by Q. And here, that is 80 minus 2Q by Q. Again, that is because quantity is what firm can easily choose to vary. So that's why the quantity is considered as the independent, namely choice variable. Okay, so that's the problem here. All right, so here I add something which is define an optimization problem. Here we need to maximize total revenue with respect to by choosing quantity. So here in this case, this maximization sign is what we call optimization argument, which tells the reader what you are actually doing. Are you maximizing or are you minimizing? And the function after that is what we call objective function. And the function underneath, the one underneath, is what we call choice variable. That reminds you, as you're expressing total revenue, it should be expressed as a function of Q. So its total revenue should be written this way to avoid any confusion. It's total revenue, now parenthesis, which is to tell you the total revenue should be expressed as a function of Q, namely Q should be your choice variable or independent variable, like this. Okay, then in order to maximize it, let's do the 2 steps. The first step is first order condition. Here, that is to take the first order derivative of your target, of your objective function, set that equal to 0. Okay, so total revenues derivative, which is actually marginal revenue, right? That is just for your reference. So here, that's not important. But the derivative of total revenue equal to 80 minus 2 by 2Q, which is 80 minus 4 times of Q. Right? That's the left-hand side of your equation. That should equal to 0, which is right-hand side of your equation, of your first order condition. So now we solve it. It's 80 minus 4Q equal to 0, which is 80 equals to minus 4Q. Move to the other side, change the sign. So Q equals to 20, which is 80 over 4. So that is the first step. So Q star equal to 20. That is a relative extremum or stationary point. Then we need to go to the second step, which is to check the second order condition to make sure you're maximizing revenue, not minimizing it, right? So here, second order derivative, that is the second order of the objective function. That's why I encourage you to define the maximization problem on the side. Then it's easier for you to check those functions. Okay, so the second order condition is to derive the second order derivative, right? And we are utilizing our first order derivative. Then we just take a further step, do another derivative of this 80 minus 4Q. So the result is minus 4 smaller than 0. That tells you the total revenue function is concave, like this. So Q star equals to 20 is a maximum. And when Q equals to 20, the total revenue is maximized.